Okay, so now we're being recorded and we can carry on. All right, it does mean that I'm stuck here a little bit because what I do is I use this pointer here to point on things on the screen so that if you're actually watching the video, you can see what I'm pointing at. If I just point like this, then you can't see that on the video. But I still walk around a bit. All right, so we were speaking yesterday about the fact that attraction makes things go around, yeah? And the electrons go around the nucleus because two reasons. They're positive and they're negative, so they attract. And there's another reason. Somebody else said it yesterday. They got energy. They got energy. Think about this. If you were running down the pavement and you stuck your hand out and you grabbed a lamppost as you were running past, what would happen to you? Because you were running. Okay? The moon's moving around the Earth. Why? It's been attracted and it's moving with speed. Why is it moving with so much speed? It's not moving with speed because of gravity. It's got its own momentum. Why has it got momentum? So I often show this as an example. If you want to put something into orbit, okay? Think about this. Here's the Earth, there's a mountain. You climb on top of the mountain and you throw a stone. And it falls. Now you want to put the stone into orbit, so you throw it higher and harder. Now you eat your oats and everything, and you throw it so hard that it falls and it misses the Earth. Slaps you in the back of the head. But if you duck, in orbit. Move through the moon. The Big Bang. Big Bang. Explosion, everything's flying all over everywhere. Piece comes flying past the Earth, gets trapped by the gravity. So so how do they get satellites to Mars or wherever? They use the slingshot effect. So now you're going like this, and here's a big planet, and it attracts you faster, but you're already moving fast, and then you speed you up, and then you shoot past it. Slingshot effect. You can use planets to make you go farther, faster, and further.
So the moon came from the Earth?
No. No. The moon didn't come from Earth. Okay, so now here we got two atoms. Because remember, this section of work is called bonding. Now, why would these two atoms bond? So this is an example of hydrogen. Now, what is one thing you know about hydrogen? Well, you should know. It's gas. One electron. It's in group 1. Diatomic. What does that mean? Always 2. You never find a single hydrogen on its own, ever. If you find hydrogen atoms, they're always bonded. So why would 2 hydrogen atoms like these two, why would they bond? Why would they stick together? Sorry? Electrons. Attraction for electrons. You could actually give that as the answer to every question I ask for the rest of the year. In chemistry, anyway. Attraction for electrons. Look here. For a split second, this electron is between the 2 nuclei. Don't you think you'll be attracted to that nucleus as well? Be careful if you've got good-looking friends. Don't take your girlfriend around when you've got good-looking friends, because the electrons from this atom can become attracted to the nucleus from that atom. And look here. When is this electron in between the 2? When he's in between the 2, where's the other electron? On the other side. Why? Because the electrons don't like each other. Wait till you've got a girlfriend and your best mate's got a girlfriend, and the 2 girls don't like each other. Now you go and try and have friends, go and try and make friends, and let's all go out to a movie. I'm going with her. First fight I had with my wife, before she was my wife, first fight I had with her was about my best friend and his girlfriend. I wanted her to come and watch a movie with us, and she wasn't having it. Yeah. So the electrons from this atom can get attracted to the nucleus from another atom. Okay. So what actually happens is this: the electrons are moving around so fast. So you can see there, the electrons from one atom get attracted by the other atom. But now remember, they're moving. So that's what's actually happening. And it's been shown, electron will be attracted to other atoms' protons. Now, people have talked about it like this. That's a little GIF thing that I found. 2 bulldogs, each got a bone. Now each one wants both bones, and they don't want to let go. So I often do a thing with my grade 9s. I say to them, okay, who's got a nice phone? So a guy will get a nice phone out. Who's got a nice phone? Got a nice phone, so then I grab and walk off. And normally they don't want to let go. Now, if he won't let go and I won't let go, we bonded. Yeah, that's a covalent bond. Right? Ionic bond is when I take it and I gap it and he chases me. That's an ionic one. Everywhere I go, he goes because he wants his phone back. So that's a little example of covalent bonding. Here's a GIF showing you the hydrogen bond. Now they've got too many electrons there, because it looks to me like there's 4 electrons there. We know that 2 hydrogens only got 2 electrons. But I think that's just anyway, it's supposed to only be 2 electrons. I didn't make this GIF, somebody made it. Now they're bonded because the electrons are attracted by both. And once they, your electrons look the same as my electrons. So we don't know whose electrons are whose now. They're just around everybody. So that's how a bond formed. What's happening? That's what's happening. 2 dogs, each have their own bone, won't let go. Now they're stuck together. With atoms, 2 hydrogen atoms are each attracted to their own electron, but they also attract the electrons from the other one. Now you've got this in your slide somewhere. I don't know if everything's filled in. If everything's filled in, that's fine. If there's something that isn't filled in, you might want to scribble there. I've left you space to scribble on these pages so you can remember. All right. So we're making a little bit of progress. Can I move off there? Okay, cool. So covalent bond, let's have a look in detail. What is a covalent bond? Well, it's a shared pair of electrons. And it's formed between nonmetals and nonmetals. Why is it formed between nonmetals and nonmetals? So I haven't explained this to you, but you'll see that the nonmetals attract the electrons much more strongly than the metals do. So when nonmetals bond, they all attract the electrons really strongly. Nobody's going to let go. So now they covalently bond. But when nonmetals bond with metals, it's different. The nonmetals somehow steal the electrons of the metals. They run off with them, and now the metals chase them. So that's why you get ionic bonding with nonmetals and metals. But with nonmetals, you just get covalent bonding. Sorry? Yeah. So that's your nonmetals are going to form covalent bonds. The covalent bonds are all the diatomic molecules: hydrogen, oxygen, fluorine, chlorine. You know these. These are all the diatomic ones. You've known them since grade 9. They're all covalent bonds. These guys are pure covalent bonds. Now, this year we're going to mess your heads up a little bit because we're going to talk about impure bonding. Okay, you'll still get there. Non-polar bonding. But these ones are pure covalent bonds, and pure covalent bonds means that the electrons are shared equally. Okay, because the 2 atoms are equally as strong as each other. 2 hydrogens attract the electrons with the same string. 2 oxygens attract the electrons with the same string. So it's equal sharing. You're struggling, Mr. What's it? London. Who's it? No, you Lawson. Mr. What's your surname, Josh? Bettler. You're struggling to stay awake. You had too much lunch. Too hot. Come, you need to wake up. So you get equal sharing. Now, we show these with Lewis diagrams. You probably did Lewis diagrams in grade 10. Yeah? Now we're going to get on to a little bit more complicated ones. So this is the one electron belonging to the one hydrogen. That's the other electron belonging to the other hydrogen. But now we show that they're shared by drawing them together. And you can either draw a Lewis diagram, which is this one with the electrons, the dots and the cross, or a Cooper diagram where you show the bond as a single line, single horizontal line. A shared pair of electrons is a covalent bond, one single covalent bond. And we're going to look at things that have got more than one single covalent bond. Here I'm starting to introduce some of the properties of covalent bonds. The electrons are held strongly in a bond, so they can't conduct electricity. So covalent compounds are non-conductors. Okay. And a pure covalent bond is a pure covalent bond, and it's a pure covalent single bond. All right. Let's have a look at one that's a bit different. Here we've got oxygen. Now let me show you what happens with oxygen. We'll go here first. So oxygen, how many valence electrons has it got? 1, 2, 3, 4, 5, 6. How do we know it's got 6 valence electrons? It's in group 6 on the periodic table. So that you've got to remember from grade 9. So how do they bond? Well, each oxygen has 2 unpaired electrons. Now it turns out that unpaired electrons are very unstable. So they share 1 electron each. Well, 2 electrons each. So this one pairs up with that one, and this one pairs up with that one, and then you get this situation, where you've now got 2 shared pairs, a double covalent bond. So you must be able to draw this Lewis structure for oxygen. Okay, out of your head. You don't have to show all of this business. You just have to show the. Once we draw the molecule, we put the electrons as far away from each other as possible. Now we have to put these 4 in between because they are being shared by both. But then the other electrons would be as far away as they can from each other, and they would be in pairs. Okay, and that's an oxygen molecule. That's the Lewis diagram. Over here, I've got the Cooper notation. Each red line stands for 1 covalent bond, 1 shared pair. Lewis diagram, Cooper notation, chemical formula. Happy? Now, nitrogen has a triple bond. So how does that work? Let's go and have a look. Okay, I'm not going to talk about the iron here. We're going to just move on. They have drawn nitrogen for you. Now, I see you guys all working on paper. That's fine. If you want to work on laptops, you can. Doing this kind of stuff on the laptop is quite tricky. Obviously, I've done it, so it is possible, but it just takes time. But you must be able to do it on paper. So this is a nitrogen atom, a single nitrogen atom. 5 valence electrons because it's in group 5. So each nitrogen atom has got 3 valence electrons that are unbonded. Now they can share 3. Matthew, you're struggling now. No, you have to. So we're only going to ask you for the Lewis structure for the molecule. So you have to draw 2. Yeah. So here you got 3 shared pairs, which is a triple bond. That's why nitrogen is so stable. A triple bond is almost 3 times stronger than a single bond. So you're not going to break a nitrogen molecule easily. That's why we can breathe nitrogen in all the time. Did you realize that 80% of the air that you breathe is nitrogen? Yeah. And it doesn't hurt you. It's not dangerous. Can't do anything because you can't break that bond. It's so inert that they even, do you know where you find pure nitrogen? Absolutely, because the nitrogen we're breathing here now isn't pure because it's got carbon dioxide and all the other stuff in it. Where do you find pure nitrogen? Often. You've often seen pure nitrogen. Well, you could, if you just breathe nitrogen and there was no oxygen in it, you would die. Oh, they do it in divers. They do use nitrogen. Yeah.
Really deep dive.
Yeah, because they have to balance the ratios of oxygen to nitrogen and all that kind of stuff. It's complicated. Yeah, I'm scared of that. Crisp packets. They pump your crisp packets full of nitrogen because the nitrogen won't react with the crisps and let them go stale. But if there was oxygen in there, it would react with them and they'd start going stale. So they pump pure nitrogen into the crisp packet to keep them fresh for longer. Then when you open it, it just comes in the atmosphere. It's fine. Chips, crisp. Is that? No. It's going to do the scamming. It's going to be looking after you. Okay, so that's nitrogen. You must be able to draw nitrogen's diagram. Triple bond, it's very strong, so the molecule is stable. So that's nitrogen. I've drawn it a few times. It's linear. There's a whole bunch of other diatomic molecules, and I think I've given you the full slide with all of them on. All right? But in the worksheet, you actually have to draw some of them. Now, they're all exactly the same because they're all halogens. They're all in group 7, and they've got exactly the same valence structure. So you can, if you've drawn one, you can just copy and paste it and get rid of it, change the letters. 7 electrons, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Share one covalent bond holding them all together. All right. So those are pretty straightforward. Happy? From today, you must be able to draw them. Now, what about this guy, HCl? Hydrogen's got a valency of 1, chlorine's got a valency of 1. So they can make a covalent bond. So I've done fluorine. No, here we go. Where's HCl? Oh, I didn't do HCl. Here's HCl. There's HCl. So you got a chlorine, which has got 1, 2, 3, 4, 5, 6, 7. You got hydrogen that's got 1. They share one covalent bond. Now, what I should really do is do a Cooper structure as well here. You can make HF here. HF is a very interesting compound, very dangerous compound. I'll make it for you in a second. If I do this, well, I don't have to do this. If I just get the hydrogen and the chlorine, copy paste, and get a covalent bond from there, there's the Cooper structure. Now, hydrogen fluoride would look exactly the same. Hydrogen fluoride would look exactly the same. It would just have a fluorine where I've got the chlorine. That's the bromine. Okay. You must be able to draw the Lewis diagram or the Cooper diagram. So now we want to go on to this one. Oh, I've done this one here. One of the things they often ask you to do in a test is to count the number of lone pairs. There's the molecule. How many lone pairs? 1, 2, 3, 4, 5, 6. What's this one? This is a bond pair. That's a bond pair. These are lone pairs. All right. So you need to be able to count lone pairs. All right, let's have a look at this one. Carbon can bond with hydrogen. Now, you should remember from grade 9, carbon's in group 4. Its valency is 4. Hydrogen's in group 1. Its valency is 1. So you're going to need 4 hydrogens to bond with 1 carbon. So that's how it works. Now, I think I didn't draw this one for you. I think you have to draw it on the slide. Find the slide, you'll see it's not done for you. Okay. So how does it work? Carbon's got its 4 electrons there, 1, 2, 3, 4. Then each hydrogen comes with its electron, 4 single bonds, all pointing as far away from each other as possible. Right? It's one of the few little compound molecules we expect you to be able to draw. If you understand, if you can draw the Lewis diagram, then you understand the bonding. You can't draw the Lewis diagram if you don't understand the bonding. And you can't draw the Lewis diagram if you don't know the valencies. Okay, so you must know the valencies. All right. And you've got to be able to draw either the Lewis structure or the Cooper structure for any of the molecules that I'm showing you. So, both. So this one's methane. It's pretty straightforward. Okay, we're going to still talk more about it, about its shape and all that kind of thing. But you must finish off that Lewis diagram in your notes. CH4, methane. Now, there are others that we need to go and look at. So I've just shown you the easy ones. We just rushed through them quickly. So you're not going to draw methane. Is your photographic memory working? It's all right. I hope so. You're not going to draw it either. Sorry?
I get that third piece there.
Where's yours?
I don't know.
Were you here yesterday?
Was it? I got that one.
I'll give you one yesterday. Now you lose it. Now I must give you another one. Yesterday. So there's your Lewis and Cooper structure for methane. Now we're going to do two others, well-known compounds. If you can do this one, then I'm expecting you to be able to do this one. What compound am I trying to make here? O and H. H2O. Why is there two hydrogens for each oxygen? Because there's two vacancies. There's two vacancies. So you're going to take one hydrogen, put it here, one hydrogen and put it there with its electron, H2O. Why is it NH3? Because nitrogen's got 3 valence electrons, vacant electrons, 5 valence electrons, but 3 with no pairs, and hydrogen's got 1. So you must be able to do water and nitrogen, ammonia and carbon dioxide. So there's water done for you. Oxygen, 1, 2, 3, 4, 5, 6 electrons. Each hydrogen shares 1. There's your H2O. There's your Lewis diagram. And there's your Cooper diagram.
You know, not that all 6 aren't paired up.
All 6 aren't paired up with other oxygen, with other hydrogen ones. It's always going to pair up with the minimum possible to get a full outer shell. Now remember, it's got 8. And 8 is a full outer shell.
It's 6 electrons, right?
It's got 2, 4, 6, 8. 2 of them don't belong to it. 2 of them belong to the hydrogens, but now it's kind of got 8. So it's got a full shell. So you happy with the oxygens one? Does it make sense? Now, do you draw it like this with the 2 hydrogens at 90 degrees, or do you draw it like this with them at 180 degrees? Well, actually, it doesn't matter because the molecule actually looks like this. The molecule actually looks like this. Check. So you can draw it like that, or you can draw it like this. Just depends how you're looking at it. All right. Either one is fine. I normally draw it at 90 degrees because the 2 lone pairs are there and I want to show them, but you could draw it like this. It just means you're looking at it from the end and not from the side. Happy? What about NH3? There's your nitrogen with these 5 electrons, and then you put 3 hydrogens there. So that's the Lewis diagram, and that's the Cooper diagram. And when you finish those two, we're done. Say again? I'm struggling to hear you. We'll get there next lesson. Unless you want me to carry on going. Thank you, gentlemen. Please finish up to the end of ammonia before you leave. Yeah.
You drawing these like
Yeah.
how the electrons go outside. Do you group like 2 electrons before, or do you have? I know you're meant to start with 2. Then do you like go 1 electron, then 1 electron, then 1 electron, and then keep going around until you?
Okay, so
like
when you, so let me show you. When you're doing, yeah, but there's a reason. So watch out. When you're doing. No. When you're doing an individual atom, you normally go 1, 2, 3, 4, 5, 6, 7,
Yeah.
or whatever. Now that shows you, let's say there's another one, 1, 2, 3, 4, 5. Sorry, you go 1, 2, 3, cheers, you. 4, 5, 6.
Yeah.
Now you say, okay, how's this going to bond? Once they bond, they can all move. So now you know that these two were paired already. So now they're going to be paired in the new situation where you go like this. Oh, and you know it's going to pair with those two here. And you know these two were paired, you must put them together. And you know these two were paired, you must put them together.
I'm talking about like these ones. So like say on oxygen here, ignoring that side though.
Yeah.
It's like that. Do you
must
after
put them-
after they've bonded, do you put those two together?
Yes, you must.
And these two together?
Yeah, they're always going to be in pairs.
Okay.
They're never going to be on their own. They're never going to sit like this.
Okay.
The reason they're bonding is because those ones don't want to be on their own. And now what I'm showing you here is that those are involved in bonding, and these are kind of like it. They go as far away from each other as they can. We're still going to do more on that, and you'll see why.
Okay.
But the electrons, they repel.
Thanks.
Okay, no problem.